This video presents Poisson's equation and Laplace's equation for electrostatic fields. In this video, we will review several concepts. The first is Poisson's equation, which is an example of a non-homogeneous differential equation, and Laplace's equation, which is the homogeneous version. And we will use Laplace's equation to solve a very simple example at the end. So we begin this discussion with Poisson's equation. And to arrive at this equation, we consider Gauss's law. So Gauss's law says that the divergence of the electric flux density field D is equal to the volumetric charge density rho sub V. Now we know that there's a constitutive relation between the electric flux density field D and electric field E through this relation, assuming that we are in free space. So if we substitute this into Gauss's law and rearrange things a little bit, we arrive at this divergence relation for E. We also know that the electric field E is related to the potential V through gradient. So we have this additional relation that we can now substitute back in to the relation that we have here for Gauss's law. Doing so results in this second order differential equation that we see here, where we now need to take the divergence of a gradient. This is not as hard as it seems, because we already know how to write, for example, the gradient of V, which we can do here. So there's a gradient operation on the right. And now we want to dot that with another gradient operator, or basically take the divergence. So I can just put another gradient operator on the left and a dot in the middle. And now we need to compute this dot product. So we know we compute dot products by taking the x component of each, multiplying them together, taking the y component of each, multiplying them together, and adding it to the result for the x component, and finally the same thing for the z component. So after we carry out this simple dot product, we arrive in Cartesian coordinates at this relation for divergence of gradient of v. And we usually abbreviate that with this del squared. And del squared is called the Laplacian operator, and we're going to be using it a fair amount to solving these problems. So now we have the second order non-homogeneous differential equation. It's not homogeneous because the right-hand side here is non-zero. So it's a function of the charge distribution. Now it's important to realize that the Laplacian operator looks different in the various coordinate systems. So here is Laplacian in Cartesian coordinates. We just derived that by successively applying divergence and then gradient. But in cylindrical coordinates, it has a different form, slightly more complex form. And in spherical coordinates, it's even longer. So be aware of the fact that the Laplacian operator appears differently in the various coordinate systems, much like divergence and gradient and curl do. Okay, so here's an example of a problem that we would like to solve. We have a volumetric charge density contained within a volume V, and the volumetric charge density is rho sub V as usual. And at some point P, we are interested in finding some field quantity, such as the voltage at point P or the electric field at point P. So from what we've just seen, we know that Laplace's equation applies, and if we can solve this equation, given this volumetric charge density, rho sub V, we can find V, and from V we know that we can then find E by going backwards. So this is a challenging problem to solve, or more challenging to solve, because it is again a non-homogeneous differential equation. And it would be easier to solve if the right-hand side were zero. In fact, the right-hand side is zero in many parts of this problem. If I take this field point, or this observation point, and I move it outside V, so let's say I move it outside of this volume to this point shown here, then actually at that point, there is no volumetric charge density. So the right-hand side is zero, and we get the homogeneous equation that we're looking for. So that equation, where the right-hand side is zero, is called Laplace's equation. So it is a special case of Poisson's equation, and it holds everywhere outside the source region. So everywhere outside this volume V, our problem reduces to solving this homogeneous differential equation, and it basically turns into a boundary value problem. It's important to also realize that we can apply the same concept to many other charge distributions, not just volumetric charge distributions. So the same is true in turning Poisson's equation into Laplace's equation if we had a surface charge density or a line charge density, or even a discrete distribution of point charges, so long as our observation is not coincident with the charge density itself or the point charges in the case of a discrete distribution, we can turn the problem into solving Laplace's equation. And even with a combination of volumetric, surface, line, and discrete charge distributions, we can apply the same concept. So let's apply this to a simple problem of a parallel plate capacitor. We've studied a problem like this before in the context of knowing the charge density on these plates, but we're going to approach this a little differently now. So let's say that we have two charged plates, one at y equals a, which has a voltage V of a on it, and that voltage is known, and another plate at y equals b, again with some known voltage V of b on it. And our question is, what is the voltage and corresponding electric field in this region? So we would like to know, for example, what is the voltage in this area here. Okay, so we begin by having a look at Laplace's equation. So Laplace's equation applies everywhere here where we are not on one of these two equipotential lines, right? Because we know that there must be a charge distribution on y equals a and a charge distribution on y equals b. So long as we're not focused on what is the voltage on those points, and in fact we know what the voltage is already on those points, away from those points we are trying to solve Laplace's equation. Now we can clearly work in Cartesian coordinates for this problem. So if we expand the Laplacian operator, we know that we have the second derivative of v with respect to x plus the second derivative of v with respect to y plus the second derivative of v with respect to z, and that must be equal to 0. But in this problem, there's only variation in the y direction, so we don't need to worry about these two derivatives here. So now we can integrate both sides. So if I integrate both sides once, then I would just get the first order derivative of voltage with respect to y, and the right hand side must turn into a constant. Let's call that constant a. And then if I differentiate again to get just plain v, then I should get a times y plus another constant b. So the question or problem becomes now finding these two unknown constants a and b. But we know the voltage at these two positions. Maybe we'll simplify things a little bit and call this v sub a, and this upper voltage here v sub b. So let's now substitute in various points. So let's evaluate the voltage first of all at y equals a. Well, we know that voltage is equal to v sub a, and this would be equal to a times lowercase a plus b. And so we have now one equation, and we have two unknowns to solve for. But we also know that if we evaluate the voltage at y equals b, this is also equal to vb. And this would be equal to a times lowercase b plus b. So now we have two equations and two unknowns. And we can proceed to solve these equations for these constants a and b. To simplify our problem a bit, let's consider the fact that we actually only need to know the voltage difference between these two plates. So I can reassign the voltage on the bottom plate to be a reference, which means that it is 0 volts. And we'll say that the top plate is charged to a voltage level V0 with respect to the bottom plate. So then if I take my previous equations and, for example, evaluate V at A, we know that this is now 0 and equal to our previous equation. And so this allows us to solve for one of our constants, or propose at least an expression for one of our constants, let's say B. Then if we look at the upper plate, we know that this is also charged to a known voltage here, and we have a separate expression for that. But now we can substitute in our previous relation for B and say that this is just A times B minus A times A, or if you want, A times B minus A. And this is equal to V0. So now we can solve for one of our constants A. This constant A is equal to V0 divided by B minus A, which is the distance between the two plates. We can then substitute this back into our expression for B, which we have up above. So this is just going to be V naught over B minus A, but the negative of that because there was a minus sign out in front. So now we have a expression for voltage as a function of position Y. We substitute in our constant A, which is V naught over B minus A times Y, and then we substitute in our constant B, which is V naught over B minus A. So now we have a complete expression for these. And if we wanted, we could replace these terms in the denominator with, let's say, some value D, where D is the plate separation between these two surfaces. So now we have a complete expression for the voltage that we derived using Laplace's equation. We can proceed to find the electric field between these plates because we know that there's a gradient relation between potential and electric field. So let's do that next. So we know that electric field is minus the gradient of our potential field, and we have an expression for the potential field. First of all, we realize that there's only going to be a y component of our gradient. So we can replace our gradient with this expression here. And if I differentiate the previous expression that we derived for potential, we're just going to arrive at minus V naught over D times Y hat. So our electric field is constant between the two plates and it points in the negative Y direction or downward. So we can draw our electric field as pointing downward like this in between the two plates. And again, it is uniform and does not vary with position. And we have seen this result before when we considered two parallel charged plates next to each other. So in conclusion, Poisson's equation reduces to Laplace's equation when we are in the so-called source-free region away from the sources, which in this case is charges for electrostatic problems. This simplifies the solving for either the potential field or the electric field in the source-free region. And it basically gives us another way to solve for potential and E field in electrostatic problems. So we have one path where we use Coulomb's law or Gauss's law to find the electric field and integrate that to find voltage. Here's another way to solve problems like that. If you know the voltages already, you solve this second order homogeneous differential equation and then use the solution for V to find other quantities such as the electric field.